Hi everyone and welcome to the learning curve. In this video I will be looking at discrete probability distribution functions. Discrete probability distribution functions can be expressed in tables where we are given the possible outcomes, which are all countable outcomes, as well as their corresponding probabilities. So here we are told that if a probability distribution function can be described using this expression, P of x equal x divided by 15, x over 15, where x is equal to the discrete values of 1, 2, 3, 4, and 5, we're asked to construct a probability distribution table and hence find these three probabilities. So I'm going to construct a probability distribution table here. And to construct my probability distribution table, I'm going to call x the individual outcomes here, which are given, which are 1, 2, 3, 4, and 5. So generally, a discrete probability distribution function can be described in the form of a table, where that table lists all the possible outcomes, which are discrete, countable numbers, as well as their associated probabilities, P of x. So here we have our probability distribution function described in the form of a table, where x represents the individual outcomes, 1, 2, 3, 4, and 5, as given to us in the question. And it is now our responsibility to determine the probabilities that are associated with each of these numbers. Now we are given the probability function here, P of x equals x over 15. So all we're going to do is that we're going to substitute each of these values of x into this probability distribution function so that we can calculate the probabilities. So for example, when x is equal to 1, we're going to use 1 to replace x here in the probability distribution function so that the associated probability for an outcome of 1 is 1 over 15. So there's a 1 over 15 chance of observing an outcome of 1 in this particular data set. So the probability here would be 1 out of 15. The probability for this one is going to be 2 out of 15, because all we're doing again is that we're using the x values that were given individually to replace this x in the probability distribution function that we're given, x over 15. So next we're going to have 3 over 15 followed by 4 over 15 followed by 5 over 15. These are our probabilities that are associated with each of these discrete outcomes. Now, one of the important things to know about probability, which we call an axiom of probability, is that the total probability must add to a value of 1, always and everywhere. So essentially, if you add up these probabilities, 1 over 15, plus 2 over 15, plus 3 over 15, plus 4 over 15, plus 5 over 15, you will get a result of 1. Total probability always adds to a value of 1. The simple way to do this, to add up all of these probabilities if you wanted to prove this, is to simply add the numerator values. Because we have a common denominator of 15, we could just add the numerator values, which are 1 plus 2, which is 3, plus 3, which is 6, plus 4, which is 10, plus 5, which is 15. So the numerator adds to 15. So we will divide that sum for the numerator of 15 by the common denominator of 15. And 15 divided by 15 is 1, which is the total probability. Total probability always adds to 1 as long as we're working with a legitimate probability distribution function. So having come up with the first thing that the question asks us for, which is to construct the probability distribution table, and hence now we're going to find 1, the probability that x is less than or equal to 2 from this probability distribution function, which is described in the form of a table, a discrete probability distribution function here described in the form of a table. In many questions, you might be given a probability distribution table like this, from which you then proceed to calculate a series of probabilities. Instead of being given a function for you to derive the probabilities yourself, in other words, instead of being given a function and then asked to construct the table as we are asked in this case, in many situations you're just given the table and asked to calculate the probabilities. So for number 1 here, which is the probability that x is less than or equal to 2, the probability that x is less than or equal to 2 would be the probabilities of all the values, all the x values here, or outcomes in the data set which are 2 or lower. And the probabilities which are the outcomes rather, which are 2 or lower, would be the outcomes 1 and 2. So basically what we're going to do here is that we're going to add the probability that x is equal to 1 to the probability that x is equal to 2. So probability that x equals 1 plus the probability that x is equal to 2, and that will give us our answer. Because here we're just asked for the probability that x is less than or equal to 2. And the values of x here, which are less than or equal to 2, in other words, 2 or less, would be 1 and 2. So the probability that x is equal to 1 here is 1 over 15. So we're simply adding 1 over 15 plus the probability that x is equal to 2, which is 2 over 15. So we're adding 1 over 15 plus 2 over 15. And because our denominator is common, which is 15, we simply write back that 15 and add the numerator values 1 plus 2, which is 3. So in other words, the probability that x is less than or equal to 2 is going to be 3 out of 15 as illustrated here. So that's how we calculate probabilities like these. Very simple and straightforward. And then we go to the second question. What is the probability that x is greater than 3? So the probability that x is greater than 3 now would be the probability that x takes on a value higher than 3. And what are the values in this probability distribution table that are higher than 3? They are 4 and 5. So the probability that x is greater than 3 would simply be equal to the probability that x is equal to 4 plus the probability that x is equal to 5. Because 4 and 5 are the only values in the data set which are larger than 3. And that's what we're asked to find, the probability that x is larger than 3. So this is going to be equal to the probability that x is equal to 4, which is 4 upon 15, plus the probability that x is equal to 5, which is 5 upon 15. And again, because the denominator is common in both of these fractions, which is 15, we simply write back that 15 in the answer and add the numerators, which are 4 plus 5, and we get 9. So the probability that x is greater than 3 is 9 upon 15, and that takes care of number 2. For number 3 now, we're asked to find the probability that x is greater than 2, which is what this part here is saying, the probability that x is greater than 2, but less than or equal to 4. In other words, what are all the values that fall between 2 and 4, not including 2, because we don't have an or equal to sign here on this inequality, but including 4. So let's say that again. This is asking for the probability associated. What is the probability that x can be a value falling in the range between 2 and 4, not including 2, but including 4. So let's see what that includes here. So the probability that x is here greater than 2, but less than or equal to 4 would be equal to the probability that x is equal to 3 plus the probability that x is equal to 4, plus the probability that x is equal to 4. The reason why 2 is not included in this interval is because we are not interested in the probability that x is greater than or equal to 2. We're simply interested in the probability that x is greater than 2 but less than or equal to 4. Because of the or equal to, 4 has to be included in the range. So the values between 2 and 4, the x values here between 2 and 4, not including 2 but including 4, would be 3 and 4. So what we want is the probability associated with 3, which is 3 over 15 here, 3 out of 15, plus the probability associated with 4. And the probability associated with 4 would be 4 out of 15. And that is going to give us, again, because we have a common denominator of 15, we write it down. And then we add the numerator values. 3 plus 4 here is going to give us 7. So the probability that x is greater than 2 but less than or equal to 4 would be 7 out of 15. So that's how we compute probabilities from a probability distribution function expressed in the form of a table. Now we're asked to find the mean, variance, and standard deviation of this distribution. So we're going to work from the table, from the probability distribution table here that we derived from the information given to us. So we're going to find the mean. What is the mean or average value of x using this discrete probability distribution function? Let's start right there. So the mean, or we could say mu, the mean, and the symbol we're going to use for the mean here is mu, is equal to, always, the mean or expected value. That's what it is, mean or expected value. The mean or expected value. So let's just put here mean or expected value. Either term can be used. So we could have been asked to find the expected value instead of being asked to find the mean. So the mean would be mu or e of x. We could use any of these symbols to represent the mean. E of x representing the expected value of x, but the expected value is the same as the mean. So let's just do the calculation right here. E of x, which is the expected value of x, or we could have used mu, which is the mean here, is equal to the summation of x, p of x. So it's equal to the summation of x, p of x, which means that we're going to multiply each of the x values in the probability distribution table by their corresponding probabilities. That is 1 by 1 upon 15, plus 2 by 2 upon 15, plus 3 by 3 upon 15, plus 4 by 4 upon 15, plus 5 by 5 upon 15. And that is how we're going to actually calculate the expected value or mean here. So this is going to be the summation of, and then I'm going to open my bracket. This is our summation sign. So it's going to be summation of 1 multiplied by 1 over 15. So let's do that. It's 1 multiplied by 1 upon 15. So we put that in brackets. So we're going to put the different products in brackets for simplicity. So it's going to be plus 2 multiplied by, here, 2 over 15. So we're multiplying each x value by their corresponding probability. This is going to be plus 3 multiplied by 3 over 15. Here, 3 multiplied by 3 over 15. Then plus 4 multiplied by 4 upon 15. There, 4 multiplied by 4 upon 15. And then the final representation here in the data set is 5 multiplied by 5 over 15. And that takes care of the calculations that we need to do, and we'll close the bracket there. So when we multiply these out, 1 multiplied by 1 over 15 is going to give us 1 over 15 plus 2 multiplied by 2 over 15 is going to give us 4 over 15, because 2 can be expressed as 2 upon 1, and then we multiply numerator by numerator and denominator by denominator. So we get 2 multiplied by 2, which is 4, over 1 multiplied by 15, which is 15. And so this, by the same principle, would be 3 multiplied by 3, which is 9 upon 15. This, by the same principle again, would be 4 multiplied by 4, which is 16 upon 15. And then finally, 5 multiplied by 5 would be 25, which would be upon 15 as well. Then we're going to simplify this, again, because there's a common denominator of 15. We just write back that common denominator, and then we're going to add the numerator values. When we add the numerator values here, we're going to get 1 plus 4 plus 9 plus 16 plus 25. And that is going to give us 55 divided by 15. And 55 divided by 15 can be simplified to give us 3.67 rounded to 2 decimal places. So this 3.67 is our expected value, or mean. But because we're working with a discrete data set, this is a discrete probability distribution function, it means that we would have to approximate this value to the nearest whole number. So this would really be approximately 4, because 3.67 would not be a possible outcome in a discrete probability distribution function, because with discrete probability distribution functions, there are only whole number possibilities, there are only whole number outcomes. So the expected value of x here, or mu, which is the mean, would be equal to approximately 4. So that's how we calculate the mean from a discrete probability distribution function, or a discrete probability distribution table, in other words. It's really just a simple matter of multiplying x, as the formula dictates here, the summation of x times p of x, which means that we're multiplying the outcomes, or x values, by their corresponding probabilities as outlined here, and then we add the result. That's how we find the expected value of x, or mean. The next thing we're going to do is to find the variance. And to find the variance, the process is going to be similar. The formula for the variance is this: var of x, var representing here variance, is equal to the expected value of x squared minus the expected value of x all squared. And I'll explain the distinction between the expected value of x squared and the expected value of x all squared. There is a fundamental difference between the two, which is very important for us to understand in computing the variance. So the variance is the expected value of x squared minus the expected value of x here, all squared. All squared. Now we have a bit of this information already. We already have the expected value of x, which is roughly 4. The expected value of x is roughly 4. So we can essentially, I'm going to do the calculations here. Essentially, the expected value of x, we already worked it out to be 4. So we're going to put 4. Basically, this will be 4 squared. But what we don't have is the expected value of x squared, which is different from the expected value of x all squared. As indicated, for the expected value of x all squared, which is what this part of the formula is saying, all you need to do is to place the expected value of x that we worked out, which is 4 in this case, in the bracket, and we will square the result and subtract it from this expected value of x squared. Now, I'm going to demonstrate here how to work out the expected value of x squared in this box. So the expected value of x squared is computed using a formula similar to what we applied in computing the expected value of x right here. So the expected value of x squared, if you look at the formula for the expected value of x right here, it says the summation of x multiplied by p of x. Well, the formula for the expected value of x squared is just the summation of x squared p of x, which simply means that for the expected value of x squared, all we will do is to square the x values before multiplying by the associated probability. When we were calculating the expected value of x, we simply multiplied the x values or outcomes here in the probability distribution table by their associated probabilities and took the summation. But with this, what we're going to first do is to square those x values and multiply by their corresponding probabilities. So here it's going to be equal to 1 squared. Basically, we're just squaring these values here. 1, 2, 3, 4, and 5. So it's going to be 1 squared multiplied by 1 over 15. Yes. Then we're going to say plus 2 squared multiplied by 1 over 15. And that's how we do it. 2 squared multiplied by 1 upon 15. Yes. Then plus 3 squared multiplied by 1 over 15. As you realize here, all we're doing is squaring the x values and multiplying by the associated probability. Sorry, this should be up multiplied by 2 over 15 here. And 3 squared multiplied by 3 over 15, which is the probability associated with 3. Plus, then we go to 4 squared multiplied by 4 over 15. And finally, we go to 5 squared multiplied also by here 5 over 15. So the only difference between the expected value of x and the expected value of x squared is that we square the x values before we multiply by the associated probability when we are calculating the expected value of x squared. When we were calculating the expected value of x, we didn't do that. We simply went straight ahead and multiplied the given x values here, or the x values that we derived in this probability distribution table. We went ahead and multiplied them by their associated probabilities and then took a summation of the result. In this case, as I said, when we're finding the expected value of x squared, we first square the x value and multiply by the associated probability. So this is going to give me 1 squared is 1, and 1 multiplied by 1 over 15 is going to give us 1 over 15. So it's going to be 1 over 15 plus 2 squared is going to be 4, and 4 multiplied by 2 is going to be 8. So this is going to give me 8 over 15 plus 3 squared is 9, because it means we're multiplying 3 by itself. And 9 multiplied by 3 there is going to give us 27. So we get 27 over 15. Then we go to 4 squared is 16. And then we're going to multiply 16 by that numerator of 4. So when we multiply 16 by 4, we get 64. So this is plus 64 divided by 15. Plus, finally, 5 squared is 25. And then we multiply 25 by the numerator of 5, which gives us 125 divided by 15. So that's 125 divided by 15. And then, since the denominator is a common figure of 15, we can just write back that common denominator there. Let me just make a little bit of space here so that this can fit in nice and easy. Right there. All right. So here, 5 multiplied by 25 gave us 125 divided by 15. And when we add the numerator figures here, we're going to divide the numerator figures by 15. So adding the numerator figures here, which is 1 plus 8 plus 27 plus 64 plus 125 gives us 225. So this is 225. Oh, all upon the common denominator of 15. When we divide 225 by 15, we actually get 15, and that represents the expected value of x squared, which we now insert into the formula. So here we will get 15, and for precision, what I'm going to do for precision here is that instead of using the 4, I'm going to use the 3.67 for maximum precision. I'm going to use the 3.67 here for maximum precision. So this will be 15 minus 3.67 squared. So this is going to give me 15 minus, and when we square 3.67 here, which means, of course, 3.67 multiplied by itself, we get 13.47 rounded to 2 decimal places. And then to get the variance finally, we take 15 minus 13.47, which gives us 1.53, or roughly 2, if we approximate that to the nearest whole number. So that would be our variance. And to find our standard deviation, which is the last thing that the question asks us to find, the standard deviation is always and everywhere equal to the square root of the variance. So I'm going to say here, therefore, the standard deviation, which I can write as this, standard deviation of x is simply going to be equal to the square root of 1.53, and the square root of 1.53 will give us our standard deviation. The standard deviation gives us an indication of how widely spread or varied the values or individual outcomes in the data set are from the mean. So the standard deviation here is 1.24 approximately. And if we round that to a whole number, that would be 1. So strictly speaking, standard deviation would be 1, which means that on average, the individual outcomes in the data set will vary from the expected value or mean by a score of 1. And that is how we compute expected value, variance, and standard deviation for any discrete probability distribution function represented in the form of a table, which we derived earlier. And we also looked at how to calculate probabilities from a probability distribution function or probability distribution table. I hope you found this lesson to be very instructive. See you again soon. For more lessons in mathematics, remember to like, share, and subscribe. This channel covers mathematics at all levels: high schools, middle schools, elementary school, university mathematics, and so everyone can benefit, even persons who are just simply interested in keeping themselves sharp. The mathematics that we do in this channel helps you to think critically and to develop your sharpness of intellect. So everyone can benefit from subscribing to this channel and engaging in its content. Thank you, everyone. See you soon on the learning curve.